Welcome! In this session, we'll dive into problem number 689, maximum sum of three non-overlapping subarrays. This problem is a fascinating test of your ability to optimize solutions while working with arrays and subarrays. Let's explore the problem, analyze its challenges, and uncover efficient approaches for solving it. In this problem, you are given an array of integers called nums, along with an integer k. Your task is to find three non-overlapping subarrays of length k that have the maximum possible sum. The solution should return the starting indices of these three subarrays. If there are multiple solutions with the same maximum sum, the answer should be the lexicographically smallest one, which means the combination of indices should be sorted in ascending order. The input includes the array nums, where the size of the array is between 1 and 20,000, and each element is a positive integer between 1 and 10,000. The value of k is also constrained to be at least 1 and at most 1/3 of the array's length. The output is a list of three integers representing the starting indices of the chosen subarrays. Let's look at an example to understand the problem better. Suppose the input array nums is 1, 2, 1, 2, 6, 7, 5, 1, and k is 2. The output in this case is 0, 3, 5. Here's why. First, we calculate the sums of all possible subarrays of length 2. These subarrays are 1, 2, with a sum of 3 starting at index 0, 2, 1, with a sum of 3 starting at index 1, 1, 2, with a sum of 3 starting at index 2, 2, 6, with a sum of 8 starting at index 3, 6, 7, with a sum of 13 starting at index 4, 7, 5, with a sum of 12 starting at index 5, and finally, 5, 1, with a sum of 6 starting at index 6. From these, the three subarrays with the highest sums are 1, 2, starting at index 0, 2, 6, starting at index 3, and 6, 7, starting at index 5. Since these subarrays do not overlap, the starting indices of these subarrays are 0, 3, 5, which is the required output. Now consider another example. If the input array nums is 4, 3, 10, 9, 1, 6, 3, 8, 2, 6, and k is 2, the output is 2, 5, 7. To understand this, we calculate the sums of all subarrays of length 2. The subarrays are 4, 3, with a sum of 7 starting at index 0, 3, 10, with a sum of 13 starting at index 1, 10, 9, with a sum of 19 starting at index 2, 9, 1, with a sum of 10 starting at index 3, 1, 6, with a sum of 7 starting at index 4, 6, 3, with a sum of 9 starting at index 5, 3, 8, with a sum of 11 starting at index 6, 8, 2, with a sum of 10 starting at index 7, and 2, 6, with a sum of 8 starting at index 8. The three subarrays with the highest sums in this example are 10, 9, starting at index 2, 6, 3, starting at index 5, and 8, 2, starting at index 7. These subarrays are non-overlapping, and their starting indices are 2, 5, 7, which is the correct output. Now, let's look at the constraints for this problem. The length of the input array, n, can range from 1 to 20,000, and each element in the array is between 1 and 10,000. The value of k is constrained to be at least 1 and at most 1/3 of the array's length. Additionally, the subarrays must be non-overlapping, meaning no two subarrays can share any indices. If there are multiple valid answers, the lexicographically smallest one should be chosen. For edge cases, the problem must handle scenarios where the array length is exactly 3 times k, and when all elements are identical, the lexicographically smallest indices must be returned. Small input sizes, such as when n equals 3 and k equals 1, should also be handled correctly. To solve the problem of finding three non-overlapping subarrays with the maximum sum, we considered two approaches. First, the brute force approach. The intuition behind this method is straightforward: try every possible combination of three subarrays of length k, calculate their sums, and track the maximum sum along with the indices of the subarrays. This is done by iterating over all valid starting indices for the three subarrays, ensuring that they don't overlap. While conceptually simple, this approach is computationally expensive due to its n³ complexity, making it impractical for large input sizes. Instead, we opted for the optimized sliding window approach. The key idea here is to leverage sliding window sums and pre-compute the best subarray sums for the left, middle, and right subarrays. This approach takes advantage of the fact that the optimal solutions for the left and right subarrays can be pre-computed, allowing us to evaluate combinations efficiently in linear time. By reducing redundant calculations, this approach is both faster and more scalable for large inputs. The chosen solution uses a 3-pass sliding window strategy. First, we pre-compute the best subarray sums for the left side. By iterating from left to right, we calculate the sum of all subarrays of length k using a sliding window. As we move, we track the maximum sum seen so far and store the index of the best left subarray for each position. Next, we do the same for the right side, but this time iterating from right to left. This allows us to pre-compute the best right subarray for each position. With these pre-computations in place, we then evaluate all possible positions for the middle subarray. For each middle subarray, we combine it with the best left subarray and the best right subarray using the pre-computed results. This ensures that we efficiently find the combination of indices that maximizes the total sum. The sliding window approach is implemented with an O(n) time complexity, making it highly efficient even for large arrays. To implement the solution, we begin by calculating prefix sums to simplify subarray sum calculations. For the left subarray, we initialize a sliding window to calculate sums from left to right, updating the maximum sum and the corresponding starting index as we go. We store the best subarray starting index for each position in an array. Similarly, for the right subarray, we iterate from right to left, tracking the maximum sum and the best starting index for each position. With these pre-computations, we evaluate all possible starting indices for the middle subarray. For each middle subarray, we retrieve the best left and right subarray indices from the pre-computed arrays. Using these indices, we calculate the total sum of the 3 subarrays. If this sum exceeds the current maximum, we update the result with the indices of the left, middle, and right subarrays. This systematic approach ensures that we efficiently find the optimal solution without redundant calculations. Finally, after iterating through all possible middle subarray positions, we return the indices of the left, middle, and right subarrays that yield the maximum total sum. Comparing the brute force and sliding window approaches, the former is simpler to understand but computationally expensive, with a time complexity of O(n) cubed. The sliding window approach, while slightly more complex to implement, is far more efficient, achieving a linear time complexity of O(n). The key to its efficiency lies in pre-computing the best subarray sums for the left and right sides, which eliminates redundant calculations. This makes the sliding window approach the clear choice for handling large inputs efficiently. The main takeaway here is that pre-computations and sliding window techniques allow us to solve this problem in a scalable and optimal manner, making it a great strategy for competitive programming and real-world scenarios where performance is critical. In this problem, we're tasked with finding 3 non-overlapping subarrays of length k from a given array num such that their combined sum is maximized. To solve this, we can start with a brute force approach. First, we generate all possible subarrays of length k by iterating through the array. For each starting index, we calculate the sum of the subarray and store these sums in a list called subarray_sums. This pre-processing step helps us avoid recalculating the sum for the same subarray multiple times, improving efficiency slightly. Next, we explore all possible combinations of 3 non-overlapping subarrays. Using 3 nested loops, we fix the starting indices for the first, second, and third subarrays. The loops are set up to ensure that the subarrays do not overlap. For instance, the second subarray starts after the first one ends, and the third starts after the second one ends. This approach systematically tests all valid combinations of indices. For each combination of indices, I, j, l, we calculate the total sum of the 3 subarrays as the sum of subarray_sums, I, subarray_sums, j, and subarray_sums, l. We then keep track of the maximum sum encountered and the indices, I, j, l, that produce the sum. After iterating through all valid combinations, we return the indices that yield the maximum sum. While this approach is straightforward, its time complexity is O(n) cubed, due to the 3 nested loops. This makes it impractical for larger inputs. Key insights here include understanding the limitations of brute force. By pre-computing the sums of all subarrays of length k, we eliminate redundant calculations and save time. Additionally, the non-overlapping condition is enforced by carefully setting the range of the loops, ensuring that the second and third subarrays do not overlap with the first or with each other. To implement this approach, we rely on a few key data structures. The list subarray underscore sum stores the pre-computed sums of all subarrays of length k, allowing us to quickly access these sums without recalculating. Variables like max underscore sum and result underscore indices help us track the highest total sum and the indices, I, J, L, that produce it. For larger inputs, we can optimize this solution further. Using the sliding window technique, we can calculate the sum of each subarray in constant time as we slide the window forward. Additionally, a dynamic programming approach offers an even more efficient solution. By maintaining arrays that store the maximum sum of 1, 2, and 3 subarrays up to any index, we can reduce the time complexity to O(n). This eliminates the need for 3 nested loops, making the algorithm scalable for large arrays. The time complexity of the brute force approach is dominated by the 3 nested loops, resulting in O(n cubed). While pre-computing subarray sums takes O(n*k), it is overshadowed by the cubic complexity of the nested loops. The space complexity is O(n) due to the subarray underscore sums list, while variables used for tracking the results add only O(1) space. This gives an overall space complexity of O(n). There are several edge cases to consider. If the array is too small, such that n less than 3k, no solution exists, and we should return an empty result. If all elements in the array are negative, the algorithm still works, as it will find the least negative combination, which maximizes the sum. In cases where multiple sets of indices yield the same maximum sum, any valid set of indices can be returned as the result. To see the algorithm in action, consider the input nums equals 1, 2, 1, 2, 6, 7, 5, 1, and k equals 2. First, we pre-compute the sums of all subarrays of length k, resulting in subarray underscore sums equals 3, 3, 3, 8, 13, 12, 6. Next, we iterate through valid combinations of I, J, L, and calculate their total sums. For example, for I equals 0, J equals 2, L equals 4, the total sum is 3 plus 3 plus 13 equals 19. For I equals 1, J equals 3, L equals 5, the total sum is 3 plus 8 plus 12 equals 23. After testing all combinations, the maximum sum is found to be 23, corresponding to the indices 1, 3, 5. Thus, the output of the algorithm is 1, 3, 5. Here, we're diving into the Python implementation of the problem by defining a function called maxSum of 3 subarrays. The goal is to find the maximum sum of 3 non-overlapping subarrays, each of length k, and return their starting indices. First, we calculate prefix sums for all subarrays of length k. This is done by initializing a prefix underscore sums array, where each element represents the sum of a subarray starting at a specific index. We compute the sum of the first k elements directly, and then use a sliding window technique to efficiently compute the remaining sums by adding the next element and subtracting the previous element. Next, we set up 2 arrays, left and right, to track the indices of the maximum subarrays for the left and right directions, respectively. Starting with the left direction, we initialize max underscore index to 0 and iteratively update it whenever we encounter a subarray with a greater sum. The left array is filled such that for each index, it stores the starting index of the maximum subarray found so far. Similarly, for the right direction, we initialize max underscore index to the last index and work backwards. As we iterate, we update max underscore index whenever we find a subarray with an equal or greater sum, and the right array stores the corresponding indices. This pre-processing helps us efficiently find the indices of the best subarrays in the left and right directions later on. Now that we've built the left and right arrays, we focus on the middle subarray. The idea is to iterate through all possible starting indices of the middle subarray and check the total sum formed by the best subarrays from the left, middle, and right sections. For each middle subarray starting at index j, we use the left array to get the index of the best subarray on the left of j, and the right array to get the index of the best subarray on the right of j. The total sum is then calculated as the sum of the 3 subarrays. If this total is greater than the current maximum sum, we update max underscore sum and store the indices of these 3 subarrays in the result list. Finally, after iterating through all possible middle subarray positions, we return the result list, which contains the starting indices of the 3 subarrays that maximize the total sum. Here, we start by defining our solution class and the function maxSum of 3 subarrays, which takes an array of integers, nums, and an integer k, representing the size of each subarray. The goal is to find the starting indices of three non-overlapping subarrays of size k that maximize their total sum. First, we calculate prefix sums for all possible subarrays of size k. To do this, we initialize cursum to store the sum of the first k elements. Then, for the rest of the array, we use a sliding window technique, where we add the new element entering the window and subtract the one leaving it. These sums are stored in the prefix sums array, which will help us efficiently track the sums of subarrays as we proceed. Next, we need to identify the indices of the subarrays with the maximum sums from the left and right sides of the array. For this, we initialize two auxiliary arrays, left and right. The left array will store the indices of the maximum subarray sums as we iterate from the beginning, while the right array will store them as we iterate backward from the end. To populate the left array, we keep track of the index with the maximum sum so far and update it as we go. Once we finish building the left array, we switch to the right array. This time, we iterate from the end of the prefix sums array toward the beginning. At each step, we compare the current subarray's sum with the maximum sum found so far from the right. If the current sum is greater or equal, we update the max index. This ensures that the right array holds the indices of the maximum subarray sums when looking from the end of the array. Now that we have the left and right arrays built, we proceed to the core of the solution. We iterate through all possible middle subarrays, which start at index j. To calculate the total sum for a valid configuration of three subarrays, we use the left array to find the best subarray on the left side of j, the right array to find the best subarray on the right side of j, and the current subarray at j itself. The total sum is the sum of these three subarrays. If this total is greater than the maximum sum we've seen so far, we update the maxsum variable and record the indices of these three subarrays in the result array. Finally, after iterating through all valid middle subarrays and computing their respective total sums, we return the result array, which contains the starting indices of the three non-overlapping subarrays that maximize the total sum. This approach ensures that we effectively use the prefix sums and auxiliary arrays to achieve an efficient solution. By breaking the problem into smaller steps, we balance clarity with performance, making the code both maintainable and optimized for the given constraints. To solve the problem, we start by calculating the prefix sums of all subarrays of length k. In this example, k is 2, so we calculate the sum of the first subarray, which is nums 0 plus nums 1, giving us 3. Then, we slide the window to compute the next subarray sums. For the subarray 2, 1, we update the sum by subtracting the first element of the previous window and adding the new element, resulting in 3. Using this sliding window approach, we continue calculating for all subarrays. 1, 2, gives 3, 2, 6, gives 8, 6, 7, gives 13, 7, 5, gives 12, and 5, 1, gives 6. Collectively, these sums form the prefix underscore sums array 3, 3, 3, 8, 13, 12, 6. This array allows us to efficiently reference the sum of any subarray of length k as we move forward. Next, we calculate the left max indices array by traversing the prefix underscore sums from left to right. This array helps us track the index of the maximum sum subarray seen so far at each position. Starting at I equals 0, the maximum sum is at index 0. As we move through the array, the maximum sum remains unchanged until I equals 3, where we find a larger sum at index 3. From this point, the maximum sum shifts to index 4, and it remains there until the end of the array. The resulting left array is 0, 0, 0, 3, 4, 4, 4. This array ensures that for any position, we can quickly find the index of the maximum sum subarray to its left. Now, we compute the right max indices array by traversing the prefix underscore sums from right to left. This array identifies the index of the maximum sum subarray to the right of each position. Starting at I equals 6, the maximum sum is at index 6. As we move left, a larger sum is found at index 5, and then at index 4. From index 4 onward, the maximum sum remains at index 4 until we reach I equals 0. This gives us the right array, 4, 4, 4, 4, 4, 5, 6. With the left and right arrays in place, we can now determine the optimal selection of three non-overlapping subarrays. To do this, we iterate over the middle subarray indices and calculate the total sum using the prefix underscore sums and the indices stored in the left and right arrays. For j equals 2, the total sum is 19, for j equals 3, it is 23, and for j equals 4, it is 22. The maximum sum is 23, achieved with subarrays at indices 0, 3, 5. In the second example, where nums is 4, 3, 2, 1, 5, 6, 7, 8, and k is 3, we start by computing the prefix sums for subarrays of length k. The first subarray, 4, 3, 2, has a sum of 9. Sliding the window, subarray 3, 2, 1 gives 6, subarray 2, 1, 5 gives 8, subarray 1, 5, 6 gives 12, subarray 5, 6, 7 gives 18, and subarray 6, 7, 8 gives 21. These sums form the prefix underscore sums array 9, 6, 8, 12, 18, 21. This array provides a quick way to reference the sum of any subarray of length k as we calculate the optimal indices. To proceed, we compute the left max indices array for this example. Starting at I equals 0, the maximum sum is at index 0. As we traverse the prefix underscore sums array, the maximum sum remains at index 0 until I equals 3, where a larger sum is found at index 3. From index 3 onward, the maximum sum shifts to index 4, and then to index 5, where it remains for the rest of the array. This results in the left array 0, 0, 0, 3, 4, 5. Similarly, we calculate the right max indices array by traversing from right to left. Starting at I equals 5, the maximum sum is already at index 5, and it remains there as we move left, giving us the right array 5, 5, 5, 5, 5, 5. These arrays allow us to efficiently determine the best subarray indices for the left and right positions. Finally, we find the maximum sum by iterating over the middle subarray indices. In this case, there is only one valid middle subarray at j equals 3. Using the left and right arrays, we find that the optimal left subarray starts at index 0, and the optimal right subarray starts at index 5. The total sum is calculated as the sum of the left, middle, and right subarrays, prefix underscore sums 0 plus prefix underscore sums 3 plus prefix underscore sums 5, which equals 9 plus 12 plus 21, giving a total of 42. The maximum sum is 42, and the result is the indices 0, 3, 5, which represent the starting positions of the three non-overlapping subarrays with the highest total sum. To understand the time complexity of this solution, let's break it down into three main steps. First, we calculate the prefix sums for all subarrays of size k. This is done using a sliding window approach. The sum of the first subarray requires k time, but subsequent subarrays can be updated in constant time, 1, using the sliding window formula. Since there are n k plus 1 subarrays in total, this step takes k for the first subarray and n k for the rest. Combining these, we get n time for this step, as k is much smaller than n. Next, we compute the left and right maximum subarrays. For the left maximums, we make a single pass through the prefix underscore sums array, iterating from the beginning to the end, which takes n k plus 1, or simply n. Similarly, for the right maximums, we iterate backward through the same array, also taking n. These are the first two steps of the algorithm. Now, let's analyze the third step, where we iterate over all possible positions of the middle subarray. For each position, we use the pre-computed left and right arrays to find the best left and right subarrays. The number of possible positions for the middle subarray is n 3k plus 1, as we need to leave space for the left and right subarrays. This step involves a single pass through these positions, resulting in a time complexity of n minus 3k plus 1, which simplifies to n, since 3k is much smaller than n. When we combine the time complexities of all three steps, we have n plus n plus n, which simplifies to an overall time complexity of n. For space complexity, the largest contributor is the prefix underscore sums array, which stores the sums of all subarrays of size k. Since this array has a size of n k plus 1, its space complexity is n. In addition to the prefix underscore sums array, the solution also uses the left and right arrays. These arrays store the indices of the maximum subarray sums for the left and right directions, respectively. Both arrays have the same size as the prefix underscore sums array, which means their space complexity is also n. Alongside these arrays, we use a few constant space variables such as cur underscore sum, max underscore index, and result. Since their space usage doesn't grow with the input size, they contribute 1 to the space complexity. When we sum up the space used by the prefix _sums, left, and right arrays along with the constant space variables, the total space complexity becomes n plus 1, which simplifies to n overall. This space efficiency makes the algorithm scalable for large input sizes. To highlight the improvement of this optimized solution, let's compare it to the brute force approach. In the naive method, we would iterate over all possible combinations of 3 non-overlapping subarrays. Each of the 3 loops would run approximately n times, resulting in a time complexity of n cubed. This cubic complexity quickly becomes impractical for large arrays. In contrast, the optimized solution leverages prefix sums and pre-computed maximum indices to eliminate redundant computations. By reducing the number of passes to just 3 linear scans and a single traversal for the middle subarray, the time complexity is reduced to n. This dramatic improvement makes the solution efficient and suitable for input sizes as large as 10 to the power of 4. We can now analyze the time complexity across different scenarios. Regardless of the input, the algorithm always processes the array in a fixed number of linear passes. This means that the time complexity remains n in the best, average, and worst cases. The consistency comes from the fact that the input size n directly determines the runtime, with no additional factors like nested loops or recursion affecting it. Mathematically, the big O complexity is derived by summing up the contributions of all steps, n, for prefix sums, n, for the left and right maximums, and n, for iterating over the middle subarray. Together, this results in n. The space complexity analysis follows a similar pattern, as all auxiliary data structures scale linearly with n, leading to a total space complexity of n. This combination of linear time and space complexity is what makes the solution both optimal and practical for large datasets. When solving this problem, there are several common mistakes to watch out for. First, not handling overlapping subarrays is a frequent pitfall. Since the problem explicitly requires non-overlapping subarrays, failing to enforce this constraint will lead to incorrect results. A good solution is to carefully track the start and end indices of each subarray, ensuring their boundaries are respected. Another mistake is using a brute force approach without optimization. Iterating through all possible subarray combinations results in a time complexity of n cubed, which becomes impractical for large inputs. Instead, techniques like prefix sums or dynamic programming can help reduce redundant calculations and improve efficiency. Additionally, errors in implementing prefix sums can be problematic. Miscomputing indices or sums often results in off-by-one mistakes, so it's crucial to validate your prefix sum logic with smaller test cases before fully integrating it. Lastly, ignoring edge cases can lead to incorrect outputs. For instance, scenarios where k is very close to n, or arrays contain uniform values, should be explicitly tested to ensure your solution handles them correctly. Another common challenge is not considering negative numbers. Assuming that all array elements are positive can lead to invalid logic, especially if the input allows for negative values. To address this, you should add safeguards in your algorithm to handle negative numbers appropriately. From an interview perspective, there are several best practices to keep in mind. Start by understanding the constraints of the problem. Clarify whether inputs include only positive values or if negatives are allowed, as this can significantly impact your approach. Demonstrate optimization techniques early, such as prefix sums or sliding window methods, as these showcase your ability to reduce time complexity. When discussing your approach, make sure to communicate trade-offs. For example, you can highlight how dynamic programming provides better scalability than brute force, although it may require more memory. Proactively addressing edge cases, like very small or very large k values, can also impress interviewers. Finally, if you encounter issues during the implementation, debug out loud to demonstrate your thought process and problem-solving skills. This problem ties closely to several related problems on LeetCode. One example is the maximum subarray problem, also known as LeetCode number 53, which focuses on finding the subarray with the maximum sum. Another related problem is subarray sum equals k, or LeetCode number 560, where the goal is to find subarrays whose sums equal a given target. For a variation closer to this problem, consider LeetCode number 1031, the maximum sum of 2 non-overlapping subarrays, which simplifies the task by reducing the number of subarrays to 2. Lastly, LeetCode number 239, Sliding Window Maximum, demonstrates optimization techniques like sliding windows that are highly relevant for solving subarray problems efficiently. Exploring these related problems can help you deepen your understanding of common patterns and strategies in subarray-based challenges. There are also alternative approaches to consider when solving this problem. The sliding window technique is one such approach, offering a time complexity of O(n). This method is particularly efficient for continuous subarray problems, but it requires careful implementation to handle overlapping subarrays correctly. Dynamic programming is another powerful tool, also with a time complexity of O(n). By saving intermediate results, this approach avoids redundant calculations, although it may require additional memory. Lastly, the divide and conquer method, with a time complexity of O(n log n), is well suited for problems like the maximum subarray. However, it is more challenging to adapt this approach to problems with non-overlapping constraints. Each of these techniques has its own trade-offs, so selecting the right one depends on the specific requirements and constraints of the problem at hand. Great job following along. We reviewed the problem, broke it down, and explored efficient solutions. Remember, subarray problems often involve techniques like sliding windows and prefix sums, so practice applying these concepts in similar scenarios. Thanks for watching, and I'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!